of redshift, Ralph Blumenhagen, and he is going to be telling us about Swampland conjectures and high energy phase of quantum gravity. So Ralph, please go ahead. I'll give you a 5-minute warning and 0-minute warning. Okay, and I'll be quick about it.
Yeah, thank you very much for giving me the opportunity to speak here, and sorry for messing up on your schedule. So what I will talk about is a bit more speculative, I would say. So it follows some recent idea we put forward in this first paper we wrote in November by students in Munich, by Kneißl and Macredou, and there's an upcoming paper with Alvarez Garcia, Kneißl, Macredou, and Schlechter that hopefully we can publish this month, and this is also what half of the talk or even more will be about. Okay, so why? No, you checked it out. I mean, I can't scroll.
I'm clicking on the slides.
Perfect. Okay, thank you. Okay, so guided by quantum gravity arguments and experience from string theory, so we are dealing, so to say, with the Swampland program, and this is where the motivation and all the confirmation, so to say, and our arguments are based on. Of course, we are always facing the potential problem that string theory, as we understand it, is a background-dependent formulation of quantum gravity, and of course can therefore only be studied case by case, and this has been done very much in the past, in particular in our string phenomenology community. And this poses a potential Lamport problem. And by now we have a couple of Swampland conjectures, like also the ones that were reviewed already by Dieter and Timo, like the Swampland distance, the de Sitter Swampland, or the ADS distance conjecture, with evidence mostly from perturbative string theory, at least if you think about evidence from string theory. And so we might pose the questions whether they also hold in non-perturbative regimes, so there could still be potential loopholes in these arguments, or in other extreme situations. And what we have in mind now is a regime of string theory that is not very good, not very well understood, but it's supposed to exist, yeah, and this is the high energy phase of string theory. And the idea, of course, is also that we might turn the logic around and use already our result from the Swampland program to get an idea of what this high energy phase might look at. So let me first review a couple of Swampland conjectures, very briefly only, because I think we are all on the same page here in this conference. So there's the de Sitter Swampland conjecture, which says that the gradient of the scalar potential is larger than order 1 number times the potential itself. And there's also the Trans-Planckian censorship conjecture, which implies this boundary in the asymptotic field limit. And there's a slightly weaker condition, which might not be formulated yet as a conjecture, but just as a principle. This is by Tom Rodelius. And that's the no eternal inflation principle, which in fact imposes the weaker bound, where on the right-hand side, there's also still a power of the potential appearing, and everything is in Planck units here, so the potential is supposed to be smaller than 1. So this gives definitely a weaker bound, and it depends on the dimension of space-time you are in. And as has been shown or argued in this nice paper also by our chairman, applying the Trans-Planckian censorship conjecture to a sequence of de Sitter bubble decays led to an effective potential that marginally satisfies this bound. So this bound is, so to say, still compatible with the TCC. From a completely different direction, one of my colleagues in Munich, Geert Wali and collaborators, they were approaching the problem of de Sitter space from a slightly different point of view, not so much string theory, but they had their own picture of quantum gravity, a corpuscular theory of quantum gravity. And they introduced the concept of a quantum break time. So they were viewing de Sitter space as a coherent state of gravitons over Minkowski space, so not necessarily as a vacuum. And then the decoherence of this state, that means the quantum scattering of gravitons from the coherent states, leads to the quantum break time. And they were giving estimates how this depends on the Planck scale and age. And also here they found a dependence of space-time dimension. And so this is a quantum effect that was supposed to lead to a quantum breaking of the de Sitter space-time. And then after the Swampland conjectures were formulated by Waffer and so on, they extended this by a censorship, so that this quantum behavior should be censored by a larger classical mechanism. that, so to say, never allows quantum breaking to occur. And if you apply this for slowly rolling fields, you immediately on the nose find the no eternal inflation bound. So that's quite remarkable. So there seems to be some different rationale, so to say, behind the no eternal inflation bound if you view it from the perspective of this quantum break time approach. And we were driven by, so to say, this different framework of GIA and to see whether we can sort of apply or generalize it to string theory. So one question one can ask definitely is, can one get the usual de Sitter Swampland bound from this quantum break approach as well? And this is what we were trying to address in this first paper with Christian Kleissel and Adriana Macridou. So we had a little bit discussion recently on this, but I think what can be said now is that what we were viewing in this approach, we were following a different view of Tommy Markkanen in an older work. And he was viewing quantum breaking of de Sitter as a result of, so when you use a quasi-classical approach to quantum gravity and quantize, say, a scalar field in a de Sitter background, and then compute the vacuum expectation value of the energy momentum tensor of the scalar field in this background, you can find results that are not proportional to the metric. This means that this result cannot be absorbed in the renormalization of the cosmological constant, but rather led to what is called quantum breaking now. Okay, so if you do this for the usual Bunch-Davies vacuum in FLRW coordinates, indeed that's a general result. You find that this renormalized energy momentum tensor is proportional to the metric. So this is the usual story. So there's no back reaction. The back reaction only leads to a redefinition of the cosmological constant. But if you do the same computation in the center of the static patch, where you have an explicit horizon, then you can find a violation of this proportionality. And you could see a constant time-independent meta contribution that is not proportional to the metric. And if you would compute the back reaction of such a quantum meta component, you would find that de Sitter space is not a stable solution, so that there is a change, say, of H that precisely scales in the same way as found by Dvali and Gomez. And I think this we found very convincing, that something like this might be going on here, and we can understand quantum breaking also from this approach. Okay. So let me acknowledge fruitful discussion on this issue with the authors of this recent paper, where they also clarified some of our computations, actually, of Markkanen's computations. So we were trying to generalize this to string theory, and we were guided by the assumption, or we were generalizing the result found for field theory models, that there will also be a thermal flat space meta contribution to this quantum energy momentum tensor. And here, of course, there's a new issue. Namely, for string theory, it's known that there's the Hagedorn transition at the temperature that is proportional to the strength scale. And this is supposed to lead to a new phase of string theory, the high energy or high temperature phase, which is largely unknown. So it's not clear how the degrees of freedom look like in this new phase and how they are, by which theory they are described. So there are various proposals, say, being given in the literature, but the most recent one maybe is the topological gravity theory, as will supposedly also be reviewed or discussed in the talk by Sergei Gukov. So what we could do, and we followed Artik and Witten in this respect, is to just use your string theory partition function, thermal partition function, and to extrapolate it to ultra high temperatures. And what you then find is that the free energy only scales quadratically with the temperature, as opposed to ordinary, say, n-dimensional field theory models, where it would scale like t to the n. Yeah? And if you put all this to account, and then you compute your quantum break time, then we found two phases. So the low temperature phase, where the quantum break time behaves in the same way as derived by Guy and Dvali and so on. And there's in the high temperature phase, so beyond the phase transition, if you just use this extrapolation, you find that the quantum break time is independent of the dimension you were starting with, and it scales like essentially 1/h. And this would lead to a Swampland bound of the type that is also described by Waffa et al. In the Swampland, in the de Sitter Swampland conjecture. So that's the old result that I also have given talks on recently, but now we're moving forward. So it would be interesting to see, so this is a proposal, so to say, for how the de Sitter Swampland bound might look like in this high energy phase, a theory that we don't completely understand. So our concern was, or our question was now, can we maybe make it, nevertheless, give some confirmation of this result by doing a computation directly in the high T region? Because here the problem is that we don't know what it is. And this is mainly due to the occurrence of tachyons. So if you heat up your system for a critical temperature, the Hagedorn temperature, you find that there's a tachyon developing, and then the tachyon will condense and will hopefully lead to this new phase of string theory. But there are sort of toy models, or there have been discussions of models in two-dimensional. So this is now non-critical string theory. So you consider, for instance, type 0 string theory in 2 dimensions. These tachyons actually disappear. They become massless in this case. And a lot is known about these theories, and they can also be interpolated from low temperature to high temperature, and you have an exact matrix model description and so on. So this is a good toy model, we thought, for at least a non-critical string theory that features maybe some of the aspects of the high temperature region of general string theory. So I'm not saying that 10-dimensional string theory necessarily decays to these 2-dimensional theories, even though I think it's not excluded, to say it like this. So it could well be that what we describe here is the high energy regime of string theory. But this is maybe too far a claim at the moment. And there's a very nice theory by Horava and Kieler. That's the one that we were discussing, because we didn't want to discuss 2-dimensional theories, because we wanted to see this independence of the dimension. So, but there is a sort of M theory uplift of this 2-dimensional non-critical string theory. This is known as non-critical M theory in 3 dimensions. And there's also, so to say, a definition, a non-perturbative definition of this theory. Was given by Horava and Kieler as given by a non-relativistic Fermi liquid in 3 dimensions, where you can compute the exact partition function in the low and in the high temperature limit. And this is the theory that we were trying to use. So just a few facts about this theory. So first of all, it has a bosonic higher spin Lie algebra called W0, which contains the conformal algebra. SO3,2. We are in 3 dimensions now, and everything is in 3 dimensions. And one can compute an exact expression for the free energy. The details are not important here now, but for high T, one finds the expected 3-dimensional behavior that it scales like T to the 3rd power. Just as a side remark, this the integrated partition function is very closely related to the topological A model on the resolved conifold, just as an observation. Now, so this is a theory that is quite close, I would say, to topological theory. And even more, and now we are coming to the case that's of interest to us, in the conformal limit was argued by these 2 people that the ground state should be ADS2 cross S1 plus a massless fermion. And so they were looking for sort of an emergent space-time theory or gravity theory that admits this ADS2 cross S1 as a solution. And they found it, and also this W algebra that I was mentioning was, of course, a guide here, that the off-shell action was proposed to be the higher spin Chern-Simon theory with the following action, where this one form A is actually taking values in this infinite dimensional algebra W0. That's their proposal. And the fermionic matter field, this can be coupled, though not on the level of the action, but at least on the level of equations of motion for the matter field. And that's the one that I was writing here. So the question now is, does this theory satisfy the Swampland conjectures? Okay, as it stands, it might be a bit too restrictive. So what we were doing is we were extending this theory. So this is sort of a toy model now. not just by a fermionic field, but also by a scalar field. First of all, this fermionic field and the scalar field come in the same matter multiplet here automatically, and was set, the bosonic field was set to 0 in the paper by Uraba and Keeler. So we left it open, and you can think of the scalar field as the former tachyonic field that is now massless, that just for alpha prime to infinity does not really reach, so to say, decouples from the effective action, just in this limit, but for finite values, large temperatures, it could still be there. So, but for the moment, just see it as a toy model, as a simple thing that we can slightly extend this Uraba-Keeler theory. So we add a scalar field now. We consider it Chern-Simons plus a scalar field and couple it conformally, because this is also a conformal theory, and Chern-Simons theory is conformal, to couple it conformally to the background. So we get this curvature phi square coupling, and also from Weil symmetry, you can find that you can add a phi to the 6 coupling. So this is now our model. That's our model, and we would like to see whether we can get something that is satisfying Swampland conjectures. So the equation of motion for this theory, first you find here from the variation here of the Chern-Simons term, you find the Cotton tensor here, but indirectly, because here is the Ricci scalar, you also find an Einstein-Hilbert term. But the difference to ordinary gravity is that it's multiplied by phi square. So the Planck scale is not just an independent parameter, it's given here also by a VEF of field phi. There's no fundamental Planck scale in this model. And you also have an equation for the scalar field, of course. So the Einstein-Hilbert term reappears. A non-vanishing VEF of phi 0 of the field phi would induce a Planck scale of this form here, and noted it's negative. That's also opposed to ordinary gravity. But the nice thing is, if you include this phi to the 6 term, there exist ADS3 and de Sitter 3 solutions of this theory. And the minimum is precisely given by this combination. So kappa was the parameter, and the potential, and L is the size of ADS3 or de Sitter 3, or related to the cosmological constant. So Swampland conjectures in this case. So first of all, one can define an effective potential of this form, just to make it really evident here. This comes from the curvature term. This is the phi to the 6. And then the de Sitter, anti-de Sitter minimum is evident, so it's sitting here. Yeah. And if you integrate now out this field phi 0, this field phi set it to its expectation value, what you find is a well-known friend for gravity people. This is topologically massive gravity, where now this parameter usually is written in this way, where now the Planck scale here in front is given by the vacuum expectation value of phi 0, and it's negative, and this parameter mu is given like here. It's mu is equal to phi 0 square. So you have derived, so to say, topological massive gravity from this theory. What is known, there's a lot of known actually about TMG. So for instance, around the Minkowski solution, there's one massive propagating spin, 2 degrees of freedom with mass proportional to mu. These are old results by Desa, Jacqueline, Templeton. Okay, now, what are the properties of this ADS minimum here? So first of all, it's quite easy and straightforward to check the ADS moduli scale separation conjecture. That's quite straightforward with all the parameters that we have here. Then interesting, you can check the ADS distance conjecture. So the cosmological constant in this case is also proportional. The only mass scale in this problem is, so to say, h, which you set as a solution, and then h determines phi 0. So there's only one mass scale in the problem. So the cosmological constant is proportional to phi 0,4. And you see that it vanishes if you set phi 0 to 0, which is of course a finite distance in the moduli space. So this is opposed to our general ADS distance conjecture, where a vanishing cosmological constant is supposed to arrive at infinite distance in field space. Okay, so but let's look at the tower of massless states. Is this existing? So if A would be correct, there should be a tower of states with a scaling of this type. And if you just naively, so to say, apply the Swampland distance conjecture here, this is the form, But now the Planck scale is related to phi, it's not independent of it, so it drops out here in the exponent, it cancels. The only mass scale in the problem is phi 0 square, so you would find that the mass is proportional to phi 0 square is proportional to lambda to the power 1/2. So that looks good. This is consistent with the ADS distance conjecture. So what about the massless sort, the states becoming light? So there's no compactification here, and hence no tower of Kaluza-Klein modes. But we have as natural candidates these infinitely many higher spin fields. And for instance, so we need to know the mass of these. At least the mass of the first one is explicitly known. This has been computed by Kaleb, Deza, and Voidron. So now we have to compute the mass spectrum of topologically massive gravity around an anti-de Sitter space solution. And here it is. This is the formula they derived.
Ralph, this is your 5-minute warning.
Okay, so you see, if you send consistently, if you send mu L to 0, you precisely find the mass that you would naively read off from the potential I've shown you with the ADS minimum. Yeah, so that's also a nice consistency check. And people have also looked at higher spin fields in topologically massive gravity, or generalizations of topologically massive gravity, including higher spin fields. And if you look at these, the formulas they have, a natural conjecture for the mass of the higher spin fields would be like this. And indeed, for a large spin, this has the desired scaling. So the mass of these states scales like the one that you would have derived from the Swampland distance conjecture. It's not exponentially light. This is expected because it's at finite distance in moduli space, but it's scaling in a polynomial way with the field distance. Moreover, let me say that there exist BTZ black holes in TNG, which carry negative energy and therefore signal a non-perturbative instability of the ADS3 background. This you could interpret as being consistent with the proposed general instability of non-supersymmetric ADS backgrounds. Of course, everything is non-supersymmetric here. It's the high temperature phase, it's the supposed high temperature phase, maybe of a supersymmetric theory, but temperature by itself breaks already supersymmetry. So we are talking about a non-supersymmetric theory. So what about the de Sitter Swampland conjecture? Effectively, the potential just is flipped at the x-axis. So the picture I was showing you now led to a de Sitter maximum. So it is a maximum. And so you can check the refined de Sitter Swampland conjecture, the condition about the tachyonic mass. And with the formulas one can derive from the potential, it's satisfied, it scales in the correct way with phi 0 on the left and on the right-hand side. And it will be satisfied if, in this case, this constant that we don't know, of course, is smaller than 3/2. That looks also good. So there is an instability present here that is expected. What about quantum breaking? That's the actual reason why we were looking at this. So the first observation is that de Sitter 3 is conformally flat. So of course, it's a solution to pure conformal gravity. If this would be the whole story, this has no propagating modes. So there would not be a quantum break time because you see, Guillard and friends describe de Sitter space as a bound state or as a coherent state of excitations of modes. Yeah? And if there are no modes, then de Sitter, due to their logic, de Sitter space would be eternal. But adding this conformal scalar field changes the story. As we've seen, this leads to a massive propagating spin 2 mode. The quantum breaking could be possible in this case. And just by dimensional reasoning, it's clear we have only one scale in the problem, that's h. It should scale like 1/h to the -1. Naively, this differs from the quantum break time that you expect for a 3-dimensional theory that Guillard was deriving, m Planck/h². But if you take into account that the scaling of m Planck, like phi square, and that this is ready to h, you find the desired scaling. So this becomes this. So that's, and moreover, the censorship of quantum breaking here is just present. It's given by this tachyonic mode that you see explicitly. So what we found in this sort of still toy model, but at least a toy model that admits some computation, is that that everything is consistent with our claim that generally the quantum break time in the high energy phase should scale like h to the -1. So summary. So the results of our analysis for this toy model of the high energy phase of non-critical 3D M theories suggest it demonstrates that there's a good chance for the existence of non-standard effective gravity theories in the landscape of string theory. There's one way of interpreting it. That's, I think, already interesting enough. And moreover, it gives credence to the proposal that the high energy phase of string theory does also satisfy the Swampland conjectures, in particular the universal quantum break time conjecture that TQ is proportional to h to the -1. So using Swampland conjectures as a guide, if you want, to the high energy temperature phase, I think we see that the purely topological theory without any propagating degree of freedom might be a bit too simple a theory. So we need, at least for getting a decay of de Sitter here, if it's just purely topological, then it will stay forever. So if you want still that the Swampland conjectures are at work here, so you need propagating degrees of freedom here. And that's all I have to tell you today. Thank you.
Okay, thanks a lot, Ralph, for the very nice talk. I think Arthur has a question.
Yeah, Arthur.
Yes, I have a question concerning the very beginning of your talk, when you said that you have somehow an argument even inside the horizon, a static patch, to see that the de Sitter decays. And
yes,
matter effect. That's very confusing to me, because I would have thought that matter is a very tiny effect or small effect coming from the horizon temperature, which simply is an equilibrium.
It's a tiny effect. It's suppressed. Yes, indeed.
So how do you get around the suppression? Why is the matter effect growing?
No, I mean, the energy density scales like h to the n. This is what is written here, and h is of course here assumed to be smaller than m Planck. So this is a small disturbance, so to say, of the de Sitter solution, but it immediately implies, if you plug this energy density on the right-hand side of your Friedmann equation, that h dot cannot be 0. Maybe I don't see what problem you have.
That's somehow unintuitive to me. I mean, h, of course, in the de Sitter you have a thermal background, which does not prevent normally in normal language, it does not prevent a slightly different averaged energy and a finite and a de Sitter.
But in the moment when you have an energy momentum tensor, a quantum energy momentum tensor that is not proportional to the metric, and you plug it in to the right-hand side of your equations of motion, de Sitter space is not a solution anymore. You can only argue that you are not allowed to do that for some reason, but if you would allow it, and usually you allow it, I mean, you use the same argument here for Bunch-Davis, the usual Bunch-Davis in FLRW coordinates. You compute this thing, and then you say, oh, it's proportional to the metric, and then you say, oh, nice, it's only a redefinition of the cosmological constant.
I think by the same argument,
this is a very interesting discussion, but maybe in the interest of time, we can move it to Slack. So we have another question by Fengjun Shu.
Hi, thanks for the nice talk. I just have a quick question. You said that at least 2D non-critical string might be this high temperature phase of this type 2B string theory. I wonder, are there any indications for to make use?
One argument, I understand your question, very good. So one argument you could do is, so if you take type 2B in 10 dimensions, and it is known that the partition function, if you send t to infinity, yeah, becomes the partition function of type 0b. Type 0b in 10 dimensions. Of course, has a tachyon, is unstable, but then there were papers saying that type 0b, so by Hellerman. So if you consider type 0b in 10 dimensions and you study tachyon, you study the decay of the tachyon in that models, he was suggesting that this decays into two-dimensional type 0b. That might be an indication.
But at least two tachyon is the same tachyon. I mean, from this article written that somehow this tachyon.
I think it's the same tachyon. Yeah, if you look how the tachyon develops at a certain temperature, of course it's a winding mode, but it literally becomes in the infinite temperature limit the tachyon of type 0b in 10 dimensions. Yes.
Okay, interesting. Okay, thanks.
Yeah.
So Lars, we have time for a question if it's really quick.
Yeah, I can try to make it quick. Maybe a question about the later part. So You looked at like topologically massive gravity and there need to be like a propagating mode to have some effect. So
Yeah.
could you study a similar situation just in 2 dimensions using like JT gravity where you introduce a dilaton?
I think so, yes, indeed. I think you could also do that. Of course, it's not good to look at Einstein gravity because that's a trivial theory. So you need to be more like dilaton gravity. In the initial work, we were doing this, but then we found it more interesting, but say it this way, to consider a 3-dimensional theory, because then the result for 2-dimensional theory, you expect that it would scale in this like 1/h anyway.
Yeah.
Too simple as so to say, the evidence for our proposed scaling is a bit maybe too simple in this case. But indeed, you could in principle study that. I agree.
Yeah. So I think in JT gravity, if you work in like look at the solution in static coordinates,
Yeah.
I don't think there's a time dependence in that case. I think it's still a static solution. So it seems to be sort of counterintuitive with respect to the 3D result.
Could be, yeah.
Okay.
But you see, for our general claim about quantum breaking, at the end, we were not really using this approach by Markkanen and so on. So this was just a scaling argument that we were giving, and you have a propagating mode, and so we were effectively applying Gia's result. Yeah, just to make that sure.
Okay. I remind everyone that we have a very nice Slack channel where we can keep going all these interesting discussions. And now we have not only speaker transition, but also chair transition. So I say goodbye, and I think David is taking over.